So I worked on a few VMs in my life, and as all people do in VMs, I started with a Java VM, and then I went and participated in the V8 development, and I will be mostly talking about V8-related stuff here. And for the last 3 years, I have been working on optimizing compiler for the Dart VM. And all of these VMs I worked on, they have one thing in common, and it's complexity. Some people tend to think that complexity comes from us, VM people, trying to ensure a certain level of job security for ourselves. But that's not the case. The complexity comes in because the VMs have to run all kinds of weird code fast. Unfortunately, there is a side effect to complexity, and while VMs run all kinds of weird code fast, sometimes they suddenly run simple code slow. And because VM's complex, developers usually have no insight on why that happens and what can they do to fix it. And what I'm trying to do here is to alleviate this problem for you. Provide you with some methodology or some way of thinking about performance that would allow you to solve your problems. Just recently, I saw this question on Stack Overflow, and I monitor all kinds of social media closely, searching for people having performance problems. Somebody wrote a Cha-Cha-20 implementation in JavaScript. If you don't know what Cha-Cha-20 is, that's OK. I did not know either. So it's a cipher. Like all ciphers, it takes some bytes, and it spits some bytes out, and it does a lot of integer operations. And it looks all reasonable, and it performs reasonably fast for this developer. Like, it did 20 megabytes a second. And I don't know whether it's fast or slow because I do know cryptography, so probably it is slow, but it looks fast enough for me. But it did not look fast enough for the developer who wrote it, so he looked at the computational kernel of his cipher, and he said, oh, what if I try to eliminate the overhead of the calls inside the loop there? So he took the function that was there and just textually inlined it multiple times, like completely. And you can see it's a lot of code, so I'm not even showing the complete loop body anymore. And what would you expect? You would expect either a speed up or a neutral performance change, right? Nothing should have changed. But on Chrome, suddenly the performance dropped by a factor of 10 after doing this. And of course, nobody is very happy. I was not happy. When I saw this question, I said, something fishy is going on here for the rescue. And I looked at the benchmark, and I looked, and I looked, and I found this function. And then I put this comment with a nice use awesome ASCII art inside. And lo and behold, the performance was restored. So basically, you take this and you commit it to your repo, and the problem is solved to the next problem. So how did I know where to put this comment and what to look for? Well, that's because I worked on the V8 team. And I will keep the secret to ensure my successful consultancy career in the future. Well, let's backtrack a little bit and talk about benchmarks in general. Most people talking about JavaScript performance or talking about benchmarking something in JavaScript world, they think about gsperf.com. If you never saw this site, well, it's the best for you. But that's the place where people write benchmarks for JavaScript. So they can write some code snippets, and then the harness of GSperf runs them and plots a nice graphs. Like, for example, here, you can see that on Firefox, there is a way. So in this particular example, somebody tried to find the best way to count occurrences of the character in the string. So suddenly, there is a way on Firefox to count these occurrences that beats all other browsers and all other ways to do the same thing on Firefox. And this way is to split the string by this character and then count the lengths of the array that is returned by the split, and then subtract 1. And this provides like 9 and then 8 zeros after 9, so it's very fast, which is really counterintuitive. And another way to do it, which is relatively fast on all the browsers according to this JSPerf, is to take the string and then walk it character by character, but instead of actually using the iteration variable, you slice it again and again, producing a new string until the string is empty. Like, how on earth you come up with this way of iterating the string? I don't know. This is not taught in any university in the world. So if we were to approach this stuff naively, we would just go and switch all our loops over strings to this nice new way. But I'm saying this is not good. And not good is a politically correct way for saying bullshit. So we should doubt everything that we see on JSPerf or in any benchmark. You write the benchmark, you get results, first thing you do, you doubt it. And you don't apply it directly before you understand what actually is happening there. So let's backtrack even more. So this talk is actually going backwards from applications to the foundations instead of going from foundations to the applications. So we're trying here to measure the performance of a single operation. Well, how you do it? Well, you do it with this state-of-art benchmark driver here. You take the beginning of the benchmark, and then you do the operation, and then you subtract from the current time the beginning of the benchmark, right? What if the operation you try to benchmark is actually faster than the clock you have access to? Like, for example, I doubt that addition takes milliseconds on the current hardware, unless you're running on a very, 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 very old computer, So this state-of-art benchmark driver is an upgrade. You try to perform the same operation multiple times, and then you just divide the time spent on performing n operations to get the cost of a single operation. This is basically mathematics from the first grade. Like, you do operation n times, and you divide by n. Oh, magic happens with this. And you get the cost of a single operation. OK. It's similar to the keynote, where there was a lot of math, right? There is a lot of math here. So let's take a look at what JSPerf does to this nice string case here that we try to benchmark with a slice and stuff like that. Well, in fact, it wraps it in the auto-generated function like this. So JSPerf generates the code around the snippets you provide and compiles it dynamically using the function constructor. And if you read it all several times, or maybe one time, depending on how good you are, or maybe 0 times, if you are super good, you will notice that there is a loop here that is performed multiple times, repeating our operation here. And basically, we never reinitialize the string. We just slice it until it becomes empty. And then when I equals 1, we start the loop with an empty string. So all the operations after the first measurement of the first operation are actually costing nothing because the string is empty already. So let me repeat the mathematics. We expected to repeat the same operation n times, but what we actually did, we repeated it once, and the rest is costing us 0. If you divide it by n, well, you get c divided by n, and c is very small. And n is very large, because JSPerf repeats it thousands of times. And you get approximately 0. That's why it looks so fast, because we are misusing JSPerf. And the measurement is basically, we're measuring empty loop. And the key lesson here to take away is that you need to ensure that operation, when you repeat it, is doing the same amount of work every time. OK. So, but let's dig deeper. So the problem is you are not alone when you are running your benchmarks. There is somebody standing behind your back and looking at this. And this somebody is your browser, essentially, because the browsers are very smart. Let's take a look at this example. So here, somebody tries to measure what's the fastest way to convert an integer hidden inside the string, so a string representation of an integer, into an actual integer. And it turns out that on Firefox, the fastest way to do that is double tilde operator. So you apply tilde twice. Tilde is a bitwise negation. And then you get integer out, and this is very fast, like blazingly fast. Time to use double tilde everywhere instead of parseInt. Well, you probably already realize how this talk is going to go. I will say something, 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 and then say no. And that would be it. Our browsers and the machinery inside them is very clever, or are very clever, because we have multiple browsers. And they optimize the code as it executes. And that means our simple first-grade model does not work. We need to go to the second grade of school and realize that there are multiple costs involved. So first your application starts, your operation starts costing something. And then as the program runs, the cost changes. It actually can be more complicated. The cost changes multiple times, as some browsers have multi-tiered JITs. Like Safari has interpreter, then a compiler, then another compiler, and then another compiler. 4 compilers in total, well, counting the interpreter. And they can switch back and forth multiple times, so it's very complicated. And when you can start factoring all of this out, the mathematics really gets out of hand. And you can no longer approach it with this first-grade mathematics at all, and you have to start thinking. So you need to start thinking and try to be smarter than JIT compiler. Now I will show you how to be smarter than JIT compiler, and to show you how to be smarter than JIT compiler, I have to show you what JIT compiler actually does inside. And I will show it based on the source representation of the program. Compilers do not operate on the source representation, but showing you non-source representation of the same examples would take me more time. It basically would require me teaching you a compiler course, or at least parts of it. So let's just use the source. So we tried to measure this double tilde thing. And we wrote the benchmark. So this is kind of the JSPerf driver here, and then there is initialization here. And compilers, they are trying to do the same as you would do to your program. So just think about yourself as you were in the 2nd or 3rd grade, when you were not that established JavaScript programmer. But you had already some basic reasoning. And you know that if you have a constant here, and you use it only once here, well, you just put it there, right? It makes total sense. And then you can just evaluate this expression step by step. And that's what the compiler does at compile time. Basically, that's what compiler arrives to. It just has the assignment of a constant to a variable, and that's it. There is no actual tilde operator left anymore to execute. There is no parsing happening, so you're not measuring anything. This optimization is called constant propagation, and all JITs, even Internet Explorer, because Internet Explorer JIT is pretty good these days. Oh, it's called Edge, and now I'm outdated. So everybody does this. Here, people can become very optimistic and say, I can trick the compiler because I am smarter. And I will make it non-constant there, and it will not be able to do the constant propagation anymore. Well, yeah, it will not be able to do the constant propagation anymore, but it has more tricks in its sleeve. It would just look, I is initialized once outside the loop, and it never changes inside the loop. That means the result of applying tilde operator does not change either. And that means it will screw you up. It will go there and say, this is loop invariant. This whole expression is loop invariant. And the loop invariants can be moved out of the loop and placed before the loop, just like you would do to your code manually. And again, you end up with just assignment of some variable to a variable, essentially. And you're not measuring parsing time, because it will happen only once outside of the loop. This is called loop invariant code motion. And again, everybody does this. Without this, you cannot really reach any good performance in JavaScript. Compilers can go further. They can look at this code and say, well, it does not look like anybody is using this variable. And if nobody uses this variable, nobody needs this computation. And nobody needs this computation, that means nobody needs I. Well, hasta la vista, baby. And some compilers would go as far as just saying, well, there is a loop that does nothing but looping. Well, also, see you. So this is called dead code elimination. Not every compiler will go as far as eliminating the loops. For example, V8 right now cannot do it. But there are some new compiler infrastructure being built in V8 as we speak, or rather they sleep now because they're in Europe, but they will start building it when we sleep, which will be able to eliminate the loops as well. Remember this example with the super fast string splitting stuff on Firefox? Well, it turns out that Firefox is able to understand that splitting a string by a string and taking the length of that and doing some math on that is a dead code because the result is never used and nothing has a side effect here. So it just disappears. And that's why it's so fast and it runs with such incredible speed. Basically, if you see anything on GSperf running with speed like 6 and then 8 zeros, that means nothing is happening. It's an empty loop. And you have to reevaluate the way you write the benchmark. So what we established here is that optimizer eats all the benchmarks for breakfast, or lunch or dinner, basically all the day long and then in the night as well. You can try to develop benchmarks that are impossible for the optimizer to eat because you are still smarter than machine, right? Machines are dumber than humans, or at least for now, until Skynet comes and optimizes everything away. So my biggest suggestion, or my most common suggestion to people who ask me how to write benchmarks that are smarter than compiler is not to try to write them. Just use the real code and benchmark your real applications in production or something like that. Use your users as the experimental hamsters. So yeah, back to the topic. Here is 3 suggestions what you can do. Basically, you have to avoid the most common optimizations by avoiding constants, avoiding loop invariants, and avoiding the dead code. But the most important thing, you should verify results when you actually do benchmarking, because that already usually helps to trick certain optimizations like dead code elimination, because you're actually using values to verify them. So here's what we could do to this benchmark to avoid the problems. We could say initialize 2 strings, non-constants, and then start just swapping them in the loop to keep them non-invariant in the loop. And then you do some checking at the end, and you throw an exception if it fails. And this is not bad, but might not still be enough if your compiler is smart. For example, compilers have this sweet optimization where they say, I see the loop. What if I repeat the body twice but do twice less iterations? And then you do one additional depending on whether it's even or odd. What happens here is that if you swap twice within the body, that means you did not swap anything, right? Swaps cancel each other. And compiler propagates some values, and the loop body turns into that. So basically, you have 2 dead assignments to some variables which nobody uses, and then you have an assignment of a loop invariant. And you are not measuring anything again. This optimization is called loop unrolling, and nobody does it yet in JavaScript VMs. As far as I know, V8, for example, does not do it. But I like inducing paranoia in people, so they will become afraid of writing the benchmarks. OK. So here is the clash between micro benchmarks and VMs. And now we're switching to the second part of the talk, where I'm going to show you. So previously, I showed how VMs find bugs in your benchmarks and turn them into nothing. Now I will show you how benchmarks find bugs in the VMs. And if you don't realize that benchmarks can cause bugs in the VMs, you will get completely flabbergasted by the results. Here is somebody trying to measure a strange thing. I don't know how people come up with these ideas for JSperf, honestly. It's hard to read, but what's happening there is somebody decided to measure whether it's faster to concatenate strings defined as literals or concatenate strings saved in variables captured by a function, and then you concatenate these 2 variables. And it turns out that on V8, so this D8 thing, don't be scared by it. And this dollar is not a dollar, so it's not money, but it's a shell prompt. So the D8 thing is just a standalone version of V8, which is running outside of the browser. It's kind of like Node.js, but without Node, just JS. I wrote this standalone benchmark and I ran it, and it turned out that the inside, so when you define the string literals outside of the function, then you concatenate variables inside the function, is quite a bit faster outside. And inside, when you just concatenate string literals, is slower, which is completely counterintuitive because you just concatenate literals, right? It should be faster, should be constant folded. So I managed to fight my instinct to move all my strings out of functions and kept them down. And I started looking what happened with my patented glaze. So I expect that both variants should be completely dead code eliminated or at least constant folded. So there is a tool to look at these things that I wrote in Dart advertisement. So it's very paradoxical. So, if you click on this link, unfortunately right now only I can click on this link, but if you just Google this, you will find it. So it's a tool to see the intermediate representation used by the optimizing compiler inside V8. All the things that I'm showing to you here available as links inside this tool. So you just click on it, and it downloads the stuff, and it shows you. It's completely browser-based. It has no server-side components, stuff like that. OK, let's take a look why outside is so much faster. So this is the tool. So there is a URL there. You can go on my site and find it deployed there. And the example is sitting here. So I just do click. And then you see this kind of nice UI. Oh, well, you can obviously see I do zero web development, but looks nice to me. And you see the stuff that is like that was optimized when the benchmark was running on the site. And if you click on like each of these entries, they represent an optimization that occurred during the run. You click on the thing, and then you see a lot of strange stuff going on here, like all these files that came from ancient Greece and all kinds of stuff going on here. It's a little bit hard to read. So the forest of the stuff that is actually happening with the code is hidden behind all these minuscule details of the compiler implementation. So there is a all-foreseen Sauron eye there, which you can click, and it activates something called interesting mode. This interesting mode hides all the details which are irrelevant, and it splices the source of your benchmark or the source of your JavaScript function into the IR. IR stands for intermediate representation or internal representation, depends whom you talk to. And this source is right next to the instructions produced from this source. So for example, here you can see there is a loop variable decrement, and this is an addition operation there. And then there is branch, which is not a lunch and breakfast combined together, but GOTO instruction, essentially. So, and what you can see here is there is also this red line here, which signifies the loop nesting. So it's very easy to find where the action is going on in this benchmark. And if you look, and you remember that you tried to benchmark concatenation, then you discover that where the action is going on, the concatenation is definitely not going on. Like there is no concatenation inside. There is some double addition going on here for a loop variable, but no string concatenation. So outside is fast because there is nothing in there. There is empty loop. We are measuring empty loop. It is fast because it's doing nothing. So the truth is, V8 failed to constant fold the case when you had two literals together, which is counterintuitive. It was a bug which was fixed. So all the bugs that I show you here, they were fixed, maybe. So this one I, for example, fixed myself before it even was fixed in the V8. And it's pretty simple fix after you spend a couple of years in V8. But I'm not going to go into details of what's happening here. Basically, it's you can see it's like 1, 2, 3, 4, whatever, 10 lines of code, 8 lines of code, even better. And after fixing it, inside and outside, they become of the same speed. But we should remember, everything that is this fast is empty. Empty. Both are now doing nothing. So scratch this benchmark, move to the better one. What we should think, well, how the way we should think about all of this stuff is we should assume that the reasonable code we write is reasonably fast. I call this the presumption of performance, like presumption of innocence. So VM is always innocent until proven guilty. And you prove it guilty by writing reasonable benchmarks and trying to understand what happens inside. You don't prove it guilty by just jumping to conclusions. But people actually jump to conclusions all the time. So people think prototype chains are slow. And they write benchmarks to confirm it, to confirm their own assumptions about prototype chains. So for example, here we create a very deeply nested prototype chain with this awesome object.create thing. And we leave some Lisp tribute at the end for the people who like Lisp. And then we write this nice benchmark with, for whatever reason, 3 loops, because we have a lot of letters in the English alphabet. And then we hoist manually the property access, and then we pit these 2 versions together using our state-of-art benchmark driver here. And we measure first one, which does lookup on each iteration, and then we measure the second one, which caches it outside of the loop. And we see that doing many lookups is 8 times slower than caching it. Seems reasonable, right? That means we confirmed what we thought. The prototype chains are slow. OK, if we assume that this is the truth, let's make it harder. What if I patch the creation of this prototype chain and I say, instead of creating the data property, use the getter? What do you think will happen? Will it become even slower? By how much? Because people know that accessors are even slower than the normal properties. Well, it turns out it becomes 8 times faster. Like, ooh, what happened here? Voodoo magic happened. So if we look using the IR Hydra, we will discover that the property access, when it's defined as a getter, is inlined, because getter is just ultimately a function. And we are using the constant in the addition operation down there. So the actual access to the constant costs nothing. And in the case of the property, the data property defined on the prototype, we suddenly discover that there is this load name generic operation, which is actually a call. And there is no constant 10 inside. And it was not hoisted out of the loop either, because you can see this red line going on here. Well, it turns out that we were benchmarking on Node. And Node is well known for being very outdated with V8 version. And the person who wrote this benchmark, he used the even older version of Node, like from whatever, 4 years ago. And that version of V8 did not support properly the data properties defined on prototypes. It only supported immediate data properties. But it had support for getters defined on prototypes. That's why the getter was faster. So if you try in newer V8, then you see they're roughly the same speed, even without the getter trick. So, and the prototype chain traversal, as we saw, got completely looped out of the loop. There is no checks left inside for the prototype check, for stability of the prototypes. OK. And now for something completely different. This slide was there even before I saw the keynote. So this is not a plagiarizing of the keynote. It's a plagiarizing of the great British humor. So what if we run the same benchmark twice? Like, do many lookups, measure it twice, lookup and cache, measure it twice. Well, it turns out the second time, even on the new V8, it suddenly slows down by a factor of roughly 3. Like, ooh, what just happened here? Again, some voodoo happened. If we look in the IR Hydra, and I'm not going to go into details because I still want to tell you some stuff before we all out of here. Like I told you that there can be multiple optimized versions of the same function as it runs. And that's precisely what happened here. So first, V8 came and optimized the function. So if you remember what we were doing there, we were doing summation here. So we have a counter, and then we just add the constant 10 again and again to the counter. So V8 first optimized the code, assuming that the counter fits into 31-bit integer, which is called a small integer in V8, or SMI for short. Then this counter overflows, and V8 de-optimizes the code and then re-optimizes it using the int32 for the counter. That is still not enough, because we are doing enough iterations to overflow 32-bit range as well. And then it de-optimizes and produces the version with a double code inside for this counter. This de-optimizes again because we reached the end of the loop, and V8 de-optimizes when it reaches the code paths that were never executed before. This is different kinds of de-optimizations. I use color coding to signify. Like this is so-called eager de-optimization, which happens when some assumption is violated in the code, and this is so-called soft de-optimization, which happens when you reach the code path that was never executed. And then the version stabilizes and never de-optimizes again. You can see it has no special color, it's just black. But unfortunately, it's stabilized in a very strange state. So now the counter is stored as a tagged variable. So tagged is, the JavaScript is a dynamically typed language, so it has to store things, it can store things boxed, because you need a type assigned to the value. And this is called tagged in V8 due to the implementation details, which I'm not going to go into here. But to tag the number, you need to allocate a box for it. And that's precisely what happens here. So you first untag the counter. So you take the number from inside the box, convert it to the machine number, and then you do addition operation, and then you rebox it back into the box. And each time you rebox it, you allocate a new box. So that obviously costs you. That's why it's slowed down by this factor of 3. I could explain you why this happens, but I don't want to go into details because it's again the bug, and explaining bugs is not fun. It's much more fun to show you the result of these bugs, what they do to your code. Basically, this plus operation at the end of the loop was confusing the way V8 thought about the counter variable. And you could walk around it by adding toString, for example, to the counter. It's a little bit of magic happening here. The bug should be fixed now as well, so you don't need to do that to your additions. But before it was fixed, you could have walked around by doing this. So after you do this, all of them perform nice and fast, and the second run is faster than the first one, as we would expect. So now let's do the dessert. Oh, not desert. I forgot one S. So method call and function call, that is a very popular topic of discussion in our world. So somebody wanted to benchmark what is faster. This is taken from JSPerf again. A function invocation, so there is this function that does some hash computation on a string, or the method invocation. So he took, or she took, the same function and applied it, put it on the prototype of some empty object. Like it's a factory adapter trampoline known to us from Java patterns of design. Yeah, and then you just benchmark the function invocation or the method invocation. And you would assume that they would perform the same. But it turns out that the method was completely optimized away, but the function is doing very sluggishly. So somebody is calling me from Los Angeles. They hang up. OK, so I'm becoming very popular. Anyway, so why method call was faster? So I'm going to show you the workaround for this bug, but never show it to anybody else. So I just took the setup of the benchmark and I added these magical concatenations in front of it. Speed your JavaScript with this one weird trick. And lo and behold, it indeed sped it up. So again, my patented glaze. Well, it turns out that before I did that, there was no function benchmark optimized at all. For some reason, V8 was not optimizing it at all. And of course, if you don't optimize it, it will be slower than the completely optimized method benchmark. There is an explanation here, but it all boils down to yada yada stuff. And I am not going to go into details. But let's look at the code once I put these things in front of it, and it was optimized. So there is this source pane in IR Hydra, which you can use to look at the source line by line. And for example, lines that produce no code, they are grayed out, and there is some special things marking that the function call here was inlined, and so on and so forth. So it turns out that after we forced it to optimize, this thing here is completely inlined now. And if you click on the inlining marker, you will go and see the source of the inline function, which can be quite useful. And there is this strange wavy background, which is quite psychedelic, but I could not come up with a better way to show it. This basically means this line produced the code, but it was hoisted out of the loop where it was originally. That is an easy way to find the lines of code that were completely moved by the loop invariant code motion. So here, the only thing that stayed in the benchmarking loop was this stupid comparison and return undefined thing. That's because the V8 has historical luggage which prevents it from removing or moving around branches. So, but everything else that you tried to benchmark went away, and that's why it's so fast again. So this is becoming really a repetitive thing to say, but we are not measuring anything here. Move on. So can the function call be faster than the method call? Well, it turns out it can be. So as I said, I work on the Dart team, and we have a compiler to JavaScript. And that's what the compiler sometimes produces. We have this concurrent, so this is a loop, oh, this is wrong here, there should be no I, but let's ignore this. This is a loop iterating over the list. And we produce almost the JavaScript loop, but it has the concurrent modification check there, which checks that if you modify the length of the list inside the loop, then it will throw an error inside. And they came to me and said, can you make this code as fast as this code with no concurrent modification check on V8? And I said, is it slower? And they said, yes, it is slower by 18%. We would like this 18% back. And I looked at it, and I said, well, there is a solution. You just need to write it like that. Put 0, comma, and then the name of your function, and then some stuff after it. So, and they looked at me and then called the ambulance. So, well, in fact, it turns out that it actually makes it faster. Why this happens? Well, let me repeat what I did. I just got an 18% speed up by replacing method call with a function call in the code that never executes because it does never throw there. Because this particular benchmark iterates the list without changing its length. I just got the speed up by changing the code that never runs during the benchmark. Wow, I'm good. Well, it turns out that if you write the code like this, this was never executed during the benchmark run, and V8 does not know where it will go if it will be executed. Because it does not know, it has to assume that it can have arbitrary side effects. And it has to keep reloading the lengths here and reloading the lengths here and stuff like that. And that's why it is slower than not doing the check, because the rest of this has no side effects. Only this call that goes to some unknown place can potentially have side effects. So this code also was never executed, but property loads are treated specially in V8. If the property load was never executed, V8 would say this path can never be taken. This does not apply to calls for some reasons, which are quite deep, so deep that I never dived deep enough. No, I dived, but OK. Anyway, so because V8 assumes that that path can never be taken, there are no side effects left in the loop, and it can hoist all stuff away and optimize things. Like it will hoist this length load and folds away this branch. You can see it's now completely grayed out. So what I would actually recommend is to not benchmark things. And if you need to benchmark things, talk to the VM people. So thank you very much. Well, not. Wait. There was another example in the very beginning of the talk. So remember this guy here, which I sped up by the comment? Well, it turns out that if you look at it in the IR Hydra, you have this repetitively de-optimizing getBlock function. So this function is called getBlock and completely goes off the rails. And this is where the optimization happens. So IR Hydra shows you everything. And repetitive de-optimization is the case where you call me from Los Angeles and ask to file a bug in V8. So it's always a bug in V8 if it optimizes again and again and again and never stabilizes. So again, yada yada explanation of what happened there. There is a more sane workaround than the comment. I just wanted to make it funny because I know how V8 works. The sane workaround is just to truncate this value you load here from the uint32 array immediately to int32. But this bug was fixed. I fixed it. And so you basically should never assume that something is slow if it is slow and stuff like that, all these things. And I said, talk to VM people like me if you need my help. And this is a real end slide. Thank you very much.